Let us start. Thank you very much for the invitation to this prestigious series of lectures. And I was asked to give the review talk related to what is going on in the field of few-nucleon physics today. And indeed, I'm going to show you only some selected examples because it is absolutely impossible to tell about such a huge amount of different researchers which are ongoing now in a very vivid field of the few-nucleon physics. And I decided to focus on many works which we are doing in Krakow's groups because I think that somehow they are representative to what is done in the field. But of course, I will try to mention also results from other groups. And currently, our Krakow groups is relatively small, 6 persons. The principal investigator is Henryk Witała. Other investigators are Jacek Gola, Kasper Topolnicki, our PhD students, Web Chahar, and a new person in the group, Artur Ankowski, and myself. Of course, we are collaborating with many people, and results which I'm going to show were obtained within the collaborations. I'm not able to mention all collaborators, so only let me give only a few names. For a long time, we collaborate with Hiroyuki Kamada, with Wayne Polizu, with Andreas Noga, and with a group from Bochum, Evgeny Appelbaum, Hermann Krebs, Sven Heihoff, and others. And with that, I can go to my outline of my talk. In the first part, I will focus on the current status of the nuclear interaction. Especially, I will show a few informations about the current status of the three-nucleon interaction, but also I would like to mention some few ideas. This topic is related to the uncertainty quantification and efforts to build the emulators for the different processes in the nuclear physics. So the points are maybe a little bit, and also relativistic approaches related to the study of the nuclear interaction. So I think all these points are somehow related to themselves. Maybe slightly different group is the work on the electroweak processes, because there we have the new components, the nuclear current. And at the end, I would like to say a few words about the very recent hot topic in few-body physics. It is the search of quantum entanglement in nuclear systems. To introduce our group, let me say that in Jagiellonian University, we are mainly focused on processes in systems of 2 and 3 nucleons, especially in the nucleon-deuteron scattering at beam energies below the pion production threshold. So in practice, it is up to 250 MeV. And here we study the both elastic scattering and the deuteron breakup already introduced by Professor Kistren. But yeah, we are also interested in study various electroweak processes on deuteron, triton, or helium-3. And here you see only the few example, electron disintegration of deuteron, photodisintegration of triton, or interaction between the deuteron and neutrinos, but there are much more possibilities here. And the aim of our work is to check if this process, and this can be described starting from the models, possibly as much realistic as possible, of the 2-nucleon and 3-nucleon interactions, and the models of the electroweak currents. So in that sense, this part of research is called the ab-initio calculations. However, there is, of course, a deeper aim between the questions. Maybe the more general question is, how accurately can we describe the nuclear phenomena without referring to quark gluon degrees of freedom. We treat, of course, nucleons like in standard way in low energy nucleon physics. Just we have the nucleons, mesons, and so on. We are not going down to the quark level. And in some sense, all above the program and what I have shown in outline is a continuation of works by Professor Mitra. Namely, if we check for the papers of Professor Mitra, which has been already reminded us by Professor Indranil Mazumdar at the beginning of this session, you can see that he already asked the same question as we are asking now. And of course, I have to show the two seminal papers on solving the free body problem with separable potentials, is bound states, first paper from 1962, and from 1963, as he proposed the formalism for the ND scattering. That direction of research was later developed in other papers. For example, in 65, there was a paper on the neutron-neutron scattering at low energies. And in that time, of course, they worked with the separable potentials. So these potentials were relatively less complicated than what we use today. The restriction was mainly to the S and P wave sparse waves. There was a question about the tensor force. And the study focused on checking what is the dependence of binding energy or other observables or interesting features in nuclear physics, like scattering lengths, on the properties of the used interaction, mainly the interaction range or other parameters. We are now somehow continuing that, but maybe we have a little more sophisticated and realistic interactions. Moreover, in the paper from 65, I have found in acknowledgements that some part of the calculations has been done at IBM 709 computer. You can check that at that time, it was really very powerful computer. Of course, today's our mobile phones are much more efficient and has much memory and number of operations per second. And this also gives me some thoughts what the people could do if they have the tools we have today. So we should be really impressed how big progress was made at that time with without computers, I have to say, and with much simpler tools they had at their disposal. But of course, Professor Mitra didn't restrict himself only to study nucleon-neutron properties. He also worked on the relativistic approaches, and here I would like to mention the paper on the relativistic corrections to the triton binding energy. I will show you some new results in the second part of my talk. He also, in general, asked about the relativistic corrections in free body problems, also not only fermions, but also bosons. And the seminal paper of three neutrons, here, in that important paper, Professor Mitra, first of all, emphasized the role of the systems with free nucleons to study at that time was more interesting the neutron-neutron interaction. And he suggested that the three-neutron is probably more probable than the d-neutron. But unfortunately, at the time, they were able only to use, again, the simple potential, and also experimental accuracy was too low to really have the final conclusion. Professor Mitra also goes beyond free-nucleon systems. So paper on the Faddeev formalism for four-particle systems from 65, and he attacked also the electromagnetic processes. Here you see the example of the paper on the electromagnetic form factors of triton and helium-3. Of course, there was plenty other works mentioned by Professor Mazumdar, but in context of my talk, I think these papers are really worth to be reminded here. Currently, we have other tools to solve the Faddeev equations. The formalism in which we work was derived in 80s and 90s of the last century by Glekle and Vitawa and others. And what we are now doing today is we are solving the Faddeev equation. We are doing that in the momentum space in partial wave decomposition scheme. And for the start, we solve the Schrödinger equation for the deuteron. So the two-nucleon interaction is used. We get the deuteron wave function. Then we solve the Lippmann-Schwinger equation to obtain the two-body T matrix. And both these findings are used in the Faddeev equation, which is equation for the auxiliary operator T. Here you see this operator form of that equation. So the T matrix includes the nucleon-nucleon potentials. There is also the free-nucleon force, the free propagator of free nucleons, and the permutation operator, which allows us to work in the isospin formalism and treat all nucleons on the same foot. When we solve the Faddeev equation in iterative manner, you can calculate the transition amplitudes for the elastic scattering or for the deuteron breakup, and these amplitudes, the building blocks for these amplitudes are the same as for the Faddeev equation, together with the solution of the Faddeev equation. And the physical contents of this equation is just to smart grouping the different interactions between, the interactions between different nucleons in such a way that we are able to reproduce the T matrix, so the sentence of the interaction between pairs of nucleons. In total, we are taking into account all possible interactions between nucleons. Okay, and Faddeev formalism allows us to find predictions for the free body systems starting from any realistic potential which we would like to use. And the potentials which we are working, of course, based on some group of them, so-called phenomenological potentials, based on the idea of which came from Yukawa nearly 100 years ago. It was developed during the time in 70s. We have got the bond B potential, which was energy dependent, which covers multiple exchanges of bosons, and its energy independent version is called charge dependent bond. And also models of free nucleon force was built because in 70s, 80s, 90s, people realized that the free nucleon force are really very important to study the free nucleon, and Bohr nucleon systems. The plot which I'm showing here is similar to what we have seen from Professor Kistren. The energy is slightly different, 155 MeV. And again, the blue band covers the various predictions based on only nucleon-nucleon interaction. Magenta band shows the predictions in which we add the free nucleon force to the nucleon-nucleon interactions. And there are also two curves which shows, I think, the best phenomenological models used in the nuclear physics, nucleon-nucleon argon V18 interaction together with free nucleon force model Urbana-9, and CD-bond nucleon-nucleon potential together with modified Thiessen-Melbourne force. Here we see the differential cross-section for elastic nucleon-deuteron scattering and the deuteron analyzing power. And as you see, in both cases, we see improvement in data description. At these energies, this improvement is, I think, better than what Professor Kisten said, that at 108 MeV, And we can learn from that effects are energy dependent. So one have to be careful and do not restrict analysis of our systems to only one energy. The discrepancy here, which you can see, comes from the fact that the predictions are in the neutron-deuteron system and data are in the proton-deuteron system, what was already mentioned by Professor Kistre. However, if we go to other observables, here is example of the deuteron vector analyzing power T22, the situation becomes more complex and not so favorable for the models of the three-nucleon force. If we have a look again at the energy 155, for that observables, we see that the inclusion of the three-nucleon force moves at least in some ranges of the scattering angles, predictions in the opposite directions to the data. And moreover, at some scattering angles, various models of the three-nucleon force moves predictions in different directions compared to predictions without three-nucleon interaction. So for sure, situation is not clear if we use the phenomenological forces, and people tried to find something new. And the story of chiral interactions comes here. This story started with seminal Weinberg's papers at the beginning of the 90s in the previous century. And at the end of 90s, Applebaum, Glecke, and Meissner proposed the nucleon energy-independent potential in the chiral expansion, firstly at the lowest order of the chiral expansion, leading order, very soon next to leading order. And during the 25 years approximately from that time, the chiral potentials were extended to higher orders, also more groups works of them. And the current status is that the two-nucleon interaction is known up to N4LO plus order. N4LO plus means that there are all contributions up to N4LO, and there are also some contributions which are thought to be dominant at the N5LO order. And the paper, basic paper here is paper by Reinhard, Krebs, and Applebaum from 2018. The three-nucleon force which is used now is only at N2LO, and the last version was published in paper 2021. And currently there is intensive ongoing work to complete N3LO at three-nucleon force. This work is done within the LEMPIC collaboration, and currently the leading persons are Applebaum, Krebs, who derived already the operator forms of the three-nucleon force at N3LO, and Kai Hebeler, Andreas Noga, and Kasper Topolnicki, and others works now on the partial wave decomposition of that work, which is quite hard task. We are closer and closer to finish this, but still, maybe this year we will be able to close the task, but we don't know what the problems we will meet yet, so I don't want to give for sure any date. Of course, there are also other groups which derive the chiral interactions, and I would like to mention here the important work by Luca Ghirlanda, Alejandro Kliewski, our next speaker, and Michael Viviani, and also works by Maria Piarulli and team from Göteborg group. Andreas Ekström is a leading person here. If you are interested in developments of the chiral interactions, please check the review paper in Few Body Systems 2022. I stress Z forces because we are working specifically with Z models of the chiral interaction, because we believe that these models are now the most precise models on the market. And this can be checked if you see in the two-nucleon sector, so in the neutron proton and proton-proton scattering, how precisely we can describe the data. The set of data is around 4,000 data points currently, depending on the energy range, which is given in the first column. And you can see that if we add the contributions from the highest orders and finally end up at the N4LO plus, the chi-square per data is very close to 1. So it is practically, you can describe the two-body observables very well. And in practice, it seems that there is no really need to go to the higher orders of the chiral expansion in the two-nucleon sector. You can also hear, or we should also remember that the chiral interactions depend on the regularization scheme and regularization parameters. And if we are working in the relatively few orders of the chiral expansion, this can introduce some additional uncertainty to the calculations. Having the interaction in the two-nucleon system and adding the three-nucleon force, and by the way, at N2LO, the three-nucleon force has only three parameters, which are typically adjusted to the triton binding energy and currently to the cross-section for the elastic scattering nucleon-deuteron at 70 MeV. But however, there are different groups which try to use other observables for the fitting. So if we take that force, that three-nucleon force into account too, we can try to do predictions for the Haber systems. And here you see the predictions for the alpha particles, the binding energy of the alpha particle, and for the oxygen-14. In two cases, when we use two different values of the regularization parameter, lambda equal 450 MeV and 500 MeV. 400 MeV is the value of the parameter which delivers us the best description of the nucleon-nucleon interaction. So we can, of the nucleon-nucleon data. So we can think about this potential as the best on the market, but lambda equal 500 also delivers quite good description of two-nucleon system. And when we check results, we see that the binding energy for alpha particle at the highest order is very close to the experimental value for both the values of the regulator. For the oxygen-14, we see that the difference between two predictions is approximately 2%, and the deviation from the experimental result is also 2%. So we see that doing calculations with the chiral potential, one have to take into account this theoretical uncertainty coming from the fact that we don't know precisely the value of the regulator. And also we have to take into account another type of error, namely that we cut the chiral expansion at some level. This kind of uncertainty is called the truncation error. If we go to the description of the nucleon-deuteron scattering in chiral potential, we can see also the dependence of the order of the chiral order which we are using in calculations, and also on the there is the lambda dependence. Here you see the differential cross-section and deuteron analyzing power, and also the combination of some tensor analyzing powers at relatively high energy, 200 MeV. This is relatively high energy for the chiral interactions at the orders which we have up to now, so the uncertainties are relatively big. If we go to lower energies, these uncertainties are smaller. But we can see that current status is quite similar what we are seeing for the phenomenological potentials. Inclusion, the three-nucleon force gives some difference between predictions, like, for example, between dashed and solid blue curves, this is at N2LO, or dashed and solid curves at this is with nucleon-nucleon interaction at N4LO, and we still are not able to describe properly the data. The errors at this energy are relatively big. We have both, here you see the truncation errors computed using the Bayesian methods. So we have here the degrees of belief, 68% and 95%. And the gray band shows the uncertainty related to using different values of regulator. More precisely, this is the range between 400 MeV and 550, which still gives the relatively good description of the two-nucleon system. Okay, in general, we try and there is suggestion from the authors of the nuclear interaction to check all these values. So still we need some improvement, and maybe this improvement will come from the higher orders of the chiral expansion. But before I will go to that, let me mention also other ideas which are on the market. First of all, there are works on explicit inclusion of the delta degrees of freedom, already shown us in the previous talk. Here's the leading persons, I think, are Arnas Deltuva, Herman Krebs, and Maria Piarulli, but also there are others. Another hope for the precise nucleon-nucleon interaction is related to the calculations arising in lattice QCD. However, this is still under development. First attempts made at unphysical pion masses failed in predicting neutron properties. So, of course, it would be difficult to attack also the scattering in two or three nucleon systems. However, still this approach seems to be promising, and hopefully at some moment we will get the nuclear interaction from the lattice QCD. Other ideas which people try to do is try to use already developed the chiral potentials, but optimize them in some manner to describe a specific part of nuclear phenomena, for example, to describe nuclear matter or describe the nuclear structure. For example, the Jean potentials, also called opt potentials, can be examples here. Of course, one can use that, but one has to be aware of the restriction for the potentials. So one has to be very careful when we would like to use that potential beyond the field of application. Nowadays, also many groups try to use artificial intelligence to perform optimization of the parameters of interaction. But in my opinion, very often they use artificial intelligence just only as a smarter tool for interpolation or fitting method. That's of course okay, but I think we have always to think about the questions, what we can learn from that. Personally, maybe I'm too old, but personally, if I have the numerical method for interpolation, which I can really understand each step in the algorithm, I will prefer to use that than instead of the methods from artificial intelligence, which very often are somehow a black box. So this is my message to specifically to the young generation, which is of course fascinated with the artificial intelligence and using this. Of course, try to use artificial intelligence, but try to obtain real qualitative progress. Do not use this only instead of well-working numerical methods, which has been already developed and tested, but try to really do some new big quality using artificial intelligence. And finally, I wanted to mention different trials to produce the phenomenological potentials. So from time to time, you can meet the papers where people try to build, for example, the three-nucleon interaction purely phenomenologically, for example, as a set of polynomials. And I think that at this level of development of the nuclear physics, we want really to understand physics from the ab-initio rules. So I think that introducing really very phenomenological forces is not the way we should go. So please, maybe we should our efforts concentrate more on the really deriving the forces with more precise and approaches which has more insight, more connection to the physics behind them. The chiral interaction is still also during the development, and there is this ongoing discussion about the regularization of chiral forces, and also this is other issues are found, and of course people try to solve them. This is an interesting study which is now ongoing in the Ruhr University. I have the slide courtesy of Sven Heihoff from the Professor Applebaum's group. Namely, they study the contributions to the two-nucleon interaction and free LO, which are the off-shell contributions, but are related to the free off-shell low energy constants. Of course, the off-shell contributions to the potentials cannot be determined from the two-nucleon system only, but the guys there found the unitary transformation, which allows them to replace that two-body interaction by the equivalent free nucleon force and 4LO. And this is a preliminary plot from Sven, in which shows the sensitivity of the differential cross-section and 155 MeV to the different values of these off-shell low energy constants. Here you see actually the differential cross-section which is at that energy in the minimum around 0.3 millibarn per sterradian. We subtracted two nucleon force contributions. So this is why we see such small values here. And the gray curves show us predictions in the range of reasonable values of these off-shell parameters. So we see that the sensitivity is quite good. Of course, you may do the calculations without these parameters, but keep others, and then we have the black curve. We can try to fit this value to the free nucleon data, and here you see what happens if we fit, but using only nucleon-nucleon interactions. This is the orange curve, and if you add the free nucleon force, you are getting the black curve. So we see again a big sensitivity, and also the need to include free nucleon interaction, and the need to include all components at the same time, which was also stressed in the lecture by Professor Kistra. There was talk today a lot about the nucleon-deuteron breakups, so I can be relatively short here. I wanted to show you only application of the nucleon-deuteron breakup to study experimental uncertainties and how the deuteron breakup can help us to fix or to choose the value of the regulation parameter, which describes the observables in the best way. So what we did the search over the all possible configurations for the deuteron breakup. More precisely, we go through the polar angles of two detected neutrons and the azimuthal angles of one detected neutron with step of 5 degree, and in energy we go with a step of 0.5 MeV. So altogether we have nearly 5 millions of kinematical configurations. And now for each θ1, θ2, we look for the maximum of the given effect. I will show you the dependence of predictions of the regulator parameter delta over the azimuthal angle and over the energies of the detected neutrons. The formula which we use is just the difference between predictions at regulator value lambda equal 400 and 550 divided by the average of these predictions. And what we see here is the localization of this kinematical configuration with specifically big difference between predictions of both values of regulators depending on the θ1 and θ2. So we can read this plot in that way that for θ1 around 25 and θ2 around 25, we found the kinematical configurations with difference between predictions at lambda equal 400 and 550, more than 40%. So quite big. Of course, some of these configurations are totally unmeasurable. For example, the cross-section is very small, or the energies of the neutrons, of the detected neutrons are very small. So we add the additional thresholds for cross-sections and energies, and then we are in the right plot. Again, we see that some configuration with big values survive, and maybe this could be interesting for the experimentalists. From our plot, we can read also precisely what is the energy of the neutrons measured and the azimuthal angles, and finally we are able to detect such configurations. It occurs that for in the case which I'm showing here, the biggest effects come or arise in final state interaction configurations. Here you see the specific angles of detection of neutrons and the difference between predictions with two values of the regulator parameters. So it would be very interesting to have the data for such configurations. The problem of different new types of theoretical uncertainties is very challenging in chiral forces. So these truncation errors, regularization dependence, and possible others is very challenging. And currently we have few initiatives within the few body community to work on statistical methods, and some of them are focusing how to estimate the uncertainties related to theoretical predictions. Let me mention here three of them. The ISNET, Information and Statistics in Nuclear Experiment and Theory, is the community which combines the statisticians, mathematicians, computer scientists, and of course nuclear physicists. They organize workshops or schools for students. There are some papers, and this is a good place to communicate with scientists working in the field if you have any questions about some statistical methods and so on. This description is these descriptions I took from the web pages of these communities. Another, I think, important community is BAND related to the Bayesian analysis of nuclear dynamics. Very broadly, this community tries to advertise the using of the Bayesian statistics both in experimental and in theoretical work. And finally, we have also the Bayesian uncertainty quantification, errors in your EFT, BUCI. Here, this community is more focused on the work in application, in effective field theory, and part also in the ask the questions about the uncertainties which arise in effective field theory, and the ways of fixing parameters. So if you are interested, please check these places to find expert or knowledge references. Also, some software is, you can find some free software that are sometimes very sophisticated. Okay, let us now back to three-nucleon force and its three parameters, and the connected to that the problem of emulators. It was already thought that at N2LO, the three-nucleon force has only two free parameters, so-called CD and CE. So the fitting these two parameters to any data we choose is actually usually not a problem. We choose the triton, which is a very pure three-nucleon system with two neutrons and protons, so there is no Coulomb force. The calculations are very fast, so this is why people use triton. And the second parameter is, as I said, usually now fitted to the deuteron, to the differential elastic cross-section. However, if we go beyond N2LO, for three-nucleon force at N3LO, we are not expecting new free parameters. However, at N4LO, we expect 13 new contact terms. So we will meet the problem of fitting 13 free parameters to the not so big set of the data of three-nucleon forces. And of course, solving the Faddeev equations many times, which would be required in such big space of parameters, would be time-consuming. So people currently work on emulators for solving Faddeev equations. And there are now different, or not only Faddeev equations, but also in other fields. And currently there are already few emulators on the market. I tried to collect only few of them. Recently, NEC had collaborators also from, I think Alessandro was involved there, published the emulator for proton-neutron scattering at low energies. What's interesting, they also combine some machine learning tools to get improvement and faster action of these emulators. Another one worth to mention, I think, is Munoz et al., quite new from March this year. This emulator is for proton-neutron scattering, and we also published such as an emulator for the neutron scattering, and I will say a few words in the moment. But in general, we see that using such emulators speed up the calculations and especially the fitting of the three parameters, few order of magnitudes. So it is really the huge progress. And at the same time, the fact that we use some approaches is not a big problem because these approaches are usually very small and well under control. If you want to see some review of the emulators, please check this paper in Review Modern Physics. So specifically for our emulator, we tried to use it to do the calculations for three parameters at N4LO, three-nucleon force, the contact terms. We used the three-nucleon force at N2LO from the Bochum group and supplemented with the N4LO contact terms from the papers from Ghirlanda et al. Our emulators basis on the observations that the three-nucleon force acts only in the lowest partial waves, and the three-nucleon force can be splitted to the part which is parameter independent and the linear combination of different terms which comes with the free parameter. And the same can be done for the T operator. And also the base in which we solve equations can be split to two parts, one with non-vanishing values of the three-nucleon force dependent on some parameters, and the second with the remaining states. And then if you insert these observations and these splittings to the Faddeev equation and do some approximation by neglecting the higher order terms in this three-nucleon force low energy parameters, parameter dependent part, you can finally get the set of Faddeev equation. One of them is with three-nucleon force parameter 3, and the rest of them use only the one piece of the three-nucleon force dependent on the specific free parameter. So instead of so if you solve the Faddeev n+1 when n is the number of free parameters Faddeev equations, you can calculate very easily the transition amplitudes for elastic scattering and for breakup, and express them as the linear combinations of the free parameters and solution of the transition amplitudes, which you have already obtained using only the specific piece of the three-nucleon interaction. For the elastic scattering, we have also this double combination. But this is relatively easy to do, and that allowed us to find the values of the three parameters at the N4LO three-nucleon force. But this has to be treated somehow approximately because we didn't use the N3LO and N3LO three-nucleon interaction, which is not yet available. So this can change after inclusion of the three-nucleon force. But anyway, this allows us to study, for example, the correlation between the three parameters of the three-nucleon force, and we have found that some of the parameters are strongly correlated. So maybe this information will be helpful in fixing the parameters to the data at the end. And we also were able to check how important are these parameters to the observables. And here you see the examples of the differential cross-section and the analyzing power at different energies, but three of them were used to adjust the parameters, and the lowest ones, and for the highest one, 190 degree and 250 degree, we really see the predictions. So, for example, if we have a look to the cross-section at 250 MeV, we see that the adding the contact terms and 4LO pushed the predictions from this dashed curve to the dotted curve, pushed predictions from the dotted curve to the dashed curve, which is the complete calculations, and we are closer to the data, still not enough, but okay, there is a step in good direction. This also happens for the analyzing power for the higher energies. And in addition, you can see that there was a question about the AY puzzle at low energies. You see that we have got the improvement in description of the AY at low energies. So this is somehow solving a Y puzzle, but solving by just adding the new force with the three parameters. And these observations was before us already obtained by Alejandro Kijewski and his group. Going beyond the pure two and three nucleon systems, we also tried to attack the various electromagnetic reactions. And I have to be a little brief here because there is not much time. But here, of course, I have to remind that in that case, the transition amplitude is built from the leptonic part, which is known analytically because it's built from spinors and gamma matrices, and nuclear part, in which we have to calculate the matrix elements of the current operator between the initial nuclear state, which is usually the bound state, and the final scattering state. So to get this initial and final nuclear state, we can get in the same way as for the nucleon-deuteron elastic or for the nucleon proton scattering. And for the currents, we have to take into account the single nucleon current and possibly also many body currents, which will describe the interaction, the mechanism in which both nucleons are involved. Also, if we are thinking about the amplitude for the electroweak properties, we can split this amplitude to contributions arising from the plane wave. So the situation when after interaction with external photon or boson, there are no further interactions between nucleons, and the rescattering part, where in addition we also have some interactions between nucleons in the final state. And this will be important, as you can see, as you will see in a moment, the rescattering is very important in many kinematical configurations. Finally, I will skip that slide and jump immediately to the deuteron photodisintegration. In that case, at the moment, we skipped the meson exchange currents because we would like to do that, to study that process with meson exchange currents consistent with the interaction. And unfortunately, up to now, especially for the chiral forces from the Bochum group, we have no consistent currents. So at the moment, we did calculations only with a single nucleon current, but we are prepared to do that with the meson exchange currents. And here you see the example of description of the of the inclusive cross-section with the data taken from that paper at the energy of the electron 85 MeV and scattering angle 40 degree. And what we observe is that if we take the plane wave calculations and the full calculations, it means including the final state interactions, we see a big difference. So the rescattering part is very important. Of course, here you can see the proof only for that one specific kinematical configuration, but I think this conclusion is very general and we should use rescattering parts. For reactions with electroweak sounds, we also tried to apply the relativistic formalism, which was also already derived for the proton deuteron elastic scattering. In this formalism, we try to use the interaction, which is the relativistic interaction. So it means it fulfills the relativistic Schrödinger equation and reproduce the deuteron and phase shifts. This is always a problem if you work with non-relativistic interactions like argon V18 or CD bond, and you'd like to use them in relativistic calculations because they are not fulfilling the relativistic Schrödinger equation. So what people usually do is to do some transformation of the potential from the non-relativistic to the relativistic one. We are also doing that, but at the end of the day, we would always we would like to work with relativistic potential, that just to avoid uncertainties relate with the transformation. Here you see only one more example of the role of the rescattering, which is important in some part of the phase shift. This is another experimental, another example of comparison our predictions with experiments. We see some deviations here. It comes from the fact that the energy which opens here is relatively big, and probably we see the meson production channel is opened. So it is maybe too high energy for us. We have to be restricted in the transfer of the energy below the pion production threshold, whereas transfer of the momentum can be higher in case of virtual photons. But
can I just say, Professor Skibinski, there's about 8 minutes left, including discussion.
Okay. So let me be faster. Recently at the market, we have the Kharkiv potential, which was derived from the field theory, and this is totally a relativistic potential. And recently, as you can see this year, we already published it is in the archive now and under review, the paper in which we study the relativistic effects, really using the relativistic potential. We confirmed what was expected from the previous calculations already shown by Professor Kistron, that the relativistic effects are important, especially in the backward angles. This is and the elastic scattering, and as seen also in the minimum of the cross section, but at high energies around 300 MeV and 400 MeV. Below, we don't see anything. More or less, the similar picture is for the analyzing power. We also now working on the neutron electron disintegration in the totally relativistic manner. The leading person in this work are people from Ukraine, Adam Arseniev and Jan Kostylenko and Jacek Golak from our group. And here you see the preliminary result, how the relativistic calculations improve the data descriptions coming from non-relativistic blue dotted curve to the relativistic one. So still a lot of is ongoing. Also example of the process, maybe that one for the radiative pion capture. This is on Triton. This is very interesting process because in the final state we have 3 free neutrons. So this system can be used to study the three-nucleon interaction, and we see that the capture rate for this process depends both on the including final state interaction between neutrons and on the inclusion of the three-nucleon interaction, and more you can find in the paper. Okay, and I have the 3 minutes to tell about the very recent research on study entanglement in the nuclear systems. Neutrons and protons are fermions. So you can build the states of the two particles and study their spin density matrix. And you can ask yourself the question, if any processes you can find the entanglement states, by entanglement here I mean states where we have really the correlation between results of measurements of neutron and protons, like is, for example, for the famous Bell states studied a lot in the electrons or atomic systems. For Bell states, you can calculate various spin observables like spin correlations, and it can be calculated directly that Z observables should be, for example, ±1 or 0, or polarization of neutrons could be 0. And now we can ask ourselves the question if the same happens in the nuclear systems. So, for example, if we take the neutron-proton scattering, we may prepare in the initial state polarized protons and neutrons, do the scattering and measure the polarization of the final state. And we can ask if there we see entanglement in the final state. To do that, we just calculate the spin correlations, polarizations, and also we can check other properties related to that as some measures of the entanglement, like concurrence, defined here, which should be 1/2 for the Bell states, and in what we did using the argon V18 potential, we have found that the occurrence in the final state in neutron-proton scattering can be very close to this value, 0.5, this is at 100 MeV of the initial energy of the scattering, what means that in that process one can find the states which are very close to the original Bell states. You can find more information in that paper. And Henryk Witała also developed the same approach for the elastic scattering for the neutron-deuteron scattering. In elastic scattering, he found the same results. So the final entanglement between the neutron and deuteron are quite close to the Bell states. Here you see some measurements. For example, this very polarization A should be for purely entanglement state 0.5. We are getting 0.505. Here should be 1.5. We are getting 1.495, so quite close. The same happens for breakup. Henryk studied the QFS and FSI and P states, and here we see the strongly entanglement states, but not totally pure states. However, for FSI with the pair of the neutron-neutron, he found the maximally entanglement states. So he found the Bell states in the breakup of the deuteron, and in case if we study the pair of the two neutrons at the FSI configuration. Let me add also that the similar study, but in search for entanglement in deuteron, was done in Roorkee by the authors here in the group of Professor Amur Muga, and in this paper you can find the paper. And summarizing, there is a big progress in field of few nucleons. However, we still some puzzles and challenges remain. We hope for the future progress, especially for completing three-nucleon force and then free LO consistent currents. Also, the heavier systems and three-nucleon were attacked. Arnas Deltuva's four-nucleon system, Linas Lazowska's attacks the neutron alpha scattering. There are also other works related to nucleon light nuclei scattering. There are other approaches, like very interesting approach developed by Dean Lee and Ulf Meissner for nuclear lattice EFT. There is low resolution EFT derived, for example, people in Bochum work on them. And of course, much more, which I had no time to discuss, like Efimov physics, nuclear structure calculations, where we observed the tremendous progress, or study the systems with strangers. With that, I would like to thank you for your kind attention.
Thank you. I'm afraid you used your time and another 5 minutes.
I'm sorry.
I don't think that we have time. Well, let's have one question. Professor Mazumba.
No, I don't have. I just applauded.
Okay. All right. In that case, I think we move to the next speaker, Professor Kievsky.
Thank you.